Welcome to The Explainer. Today, we're diving deep into mastering a really dense but absolutely fascinating chapter of the universe. We're talking about the core relationships between motion, forces, and energy. And listen, our goal today isn't just to memorize facts. We want to take your understanding from those basic concepts all the way to perfect, gymnast-like form for your Cambridge physics exams. I want you to think of a gymnast for a second. Raw strength? Well, that just isn't enough on its own, right? It's all about perfect execution and graceful landings. Every sentence you write in an exam should be exactly like that, precise and impactful. So we're going to frame our journey today from static measurements all the way to dynamic energy transfers, making absolutely sure that your grasp of these fundamental physics concepts is rock solid. No more losing marks on the basics. And hey, speaking of perfect execution, take a look at this. Accurate measurements on a flight deck are literally what keep planes safely in the sky. It's not a suggestion, it's a requirement. Standardization isn't just some boring hoop you have to jump through for passing tests. Precise measurements of fundamental quantities are the bedrock of applied physics. Before any measurement can be made, a standard or a unit must be chosen. The SI system is absolutely crucial here. Whether you're measuring a length, an area, a volume, or a time interval, precision is everything. If you forget your units, you lose the mark. It's that simple. That exact same level of precision, that life or death exactness you see on a flight deck, is going to be our guiding principle today as we tackle these topics.
Okay, let's dive into our structured roadmap for this session. We're going to break this massive topic down into 5 logical, bite-sized chunks. First up, we'll look at measurement and motion. Second, we'll untangle mass, weight, and density. Third, we're exploring the power of forces. Fourth, we've got momentum and action. And finally, we'll bring it all together with energy, work, and power.
All right, let's kick things off with Section 1, Measurement and Motion. We need to introduce the very first, absolutely crucial distinction we have to make before things actually start moving around. Now, what's really interesting about this concept is how it perfectly separates the top-tier students from the rest of the pack. We need to perfectly separate scalars from vectors. It's a vital concept that prevents you from losing those easy marks when calculating forces. You see, many physical quantities have both a magnitude, which is just a fancy word for the size or amount, and a specific direction. These are your vectors. Velocity and force are prime examples here. On the other hand, scalars only have a magnitude with absolutely no directional component at all. Think speed or mass. Now imagine a student, let's call him Alex. Alex overloads his answers with raw physics facts, but completely ignores the command word in the exam. He rushes and writes down speed when the question clearly requires a directional velocity. Boom, marks lost. So if you're ever asked to distinguish between the two, rely on this core principle. Speed is a scalar quantity and only has magnitude, whereas velocity is a vector quantity and has both magnitude and a specific direction. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Let's step it up a notch. We know we can measure exactly how fast an object is falling using distance time and speed time graphs. Those are standard tools. But ask yourself this, what exactly is pulling it down? I want to pose this question to bridge the gap between simple, observable motion and the invisible gravitational forces that are constantly acting upon objects all around us. Think about skydivers jumping out of a plane. In the absence of air resistance, an object falls in a uniform gravitational field with a constant acceleration. We call this the acceleration of freefall. We denote it by the lowercase letter g, which is approximately 9.8 meters per second squared near the Earth's surface. Now, here is a classic exam trap that catches so many students off guard. In the air around us, a heavy coin falls way faster than a light piece of paper, right? But that's just because air resistance has a much greater effect on light bodies compared to their overall weight. But what happens in a true vacuum? No air at all? They fall at the exact same rate. Without air resistance, the acceleration due to gravity is perfectly constant for all masses. Don't let the exam trick you on this one. Moving right along to Section 2, Mass, Weight, and Density. Let's transition from observing how things move to understanding the fundamental, physical properties of the objects themselves. Okay, the crucial point here, and examiners love testing this, is the hard line between mass and weight. Do not mix these up. Mass is the raw amount of matter you have. It's measured in kilograms. Weight, however, is the actual pull of gravity on that matter. We easily calculate it using the equation W equals m times g. Because weight is a force, it's measured in newtons. Imagine a lunar astronaut jumping around on the moon. The moon has a significantly lower gravitational field strength than Earth, so the g and W equals mg is much smaller. Therefore, the astronaut's mass, the actual physical matter making up their body, remains exactly the same, but their weight, it significantly decreases. If a question asks for weight and you give mass in kilograms, you're handing your marks back to the examiner.
Building right on top of mass, we have density. Density is defined as mass per unit volume. It's the intrinsic property that determines if an object is going to float or sink in a fluid. And here's a really cool, surprising real-world example of this. Ice. Solid ice floats on liquid water simply because it has a lower density than the water it displaces. It's wild when you think about it because usually solids are denser than liquids, but it perfectly anchors the mathematical formula to something you see literally every single time you pour yourself a cold iced drink.
Let's keep the momentum going and move to our third section, the power of forces. We're going to see exactly how mass and acceleration build into forces, these invisible hands that are constantly shaping motion. A force is powerful. It can change the speed of an object, it can change its direction of travel, or it can even change its size and shape. The foundational equation here, the big one you absolutely must know, is Newton's second law. Force equals mass times acceleration, or F equals ma. This brilliant little equation tells us that acceleration is directly proportional to the applied force, provided the mass is kept constant. Conversely, if you flip it around, acceleration is inversely proportional to the mass, provided the force is constant. Bottom line, to change an object's state of motion, a force is always required. If an object is accelerating, there is a resultant force acting on it. Guaranteed. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Let's look at how these forces interact in the real, messy world. First, a steady force causes a steady acceleration. Second, more mass requires more force to accelerate. That's just common sense, right? It's harder to push a heavy car than a light bicycle. And third, when several forces act simultaneously on an object, we calculate what's called a resultant force to predict their combined effect. Because remember from earlier, force is a vector. Direction matters. If Joe pulls a ring with 100 newtons to the left and Daniel pulls with 140 newtons to the right, the resultant force isn't simply adding them up to 240. No way. It's 40 newtons acting specifically to the right. Always factor in the direction.
Now, forces don't just push and pull things in straight lines, they also turn things. They create rotational effects. Consider the stability of really tall structures. Why don't tall things tip over easily on a slope? Why are tall, top-heavy vehicles so much more likely to topple over than lower, wider ones on a sharp turn? This sets up a critical concept examiners love, the center of gravity. Take the famous Leaning Tower of Pisa. In the presence of gravity, any object behaves as if its entire mass is concentrated at one single specific point, the center of gravity. Here is the golden rule for stability. As long as a vertical line drawn straight downwards from that center of gravity falls perfectly within the footprint of the object's base, it remains stable. It will not topple. But the second that vertical line falls completely outside the base, gravity creates a resultant moment, a turning effect, that causes the object to fall over. So stability is all about the position of the center of gravity relative to the physical area of the base. Keep it low and keep the base wide. All right, Section 4, Momentum in Action. Let's accelerate the narrative here by bringing mass and velocity together, especially during collisions.
So, what is momentum? Momentum is defined simply as an object's mass multiplied by its velocity. Now, let's look at this golfer. When a golfer swings, they apply a massive force over a very short time interval. In physics, we call this creating an impulse. Impulse equals force multiplied by the change in time. But here's the magic part. It also perfectly equals the change in momentum. By applying that immense force so briefly, the golfer changes the golf ball's momentum from absolute zero to its maximum velocity almost instantly. It's a massive transfer of momentum in the blink of an eye.
And this leads us to one of the most fundamental rules in the entire universe, the conservation of momentum. Think of those clacking metal balls of a Newton's cradle sitting on a desk. The rule states that the total momentum before a collision exactly equals the total momentum after the collision. However, and this is a massive however for your exams, there is a vital caveat. Momentum is only conserved if no external forces act on the system. If you are writing this in an exam, you must specify that this happens in a closed system. If you forget to mention the closed system, meaning no external forces like friction or interfering, you will miss out on the full marks. It's all about that precise gymnast-like landing we talked about.
Finally, we've reached Section 5, Energy, Work, and Power. Let's explore the underlying currency of the universe that allows all this movement and all these forces to exist in the first place.
The grand unifying principle of physics is right here on the screen. Energy cannot be created or destroyed. It is always conserved. Energy merely transfers from one store to another. It's like moving money from a checking account to a savings account. The total amount doesn't change, just where it's kept. When a ball falls from the roof of a building, the gravitational potential energy it held quietly at the top is seamlessly transferred into kinetic energy as it drops. As the height decreases, the velocity increases. But the total energy? It remains wonderfully, perfectly constant, assuming there's no air resistance draining it away as thermal energy.
So how does energy actually move around? Mechanical working is the process of making these transfers happen. Look at the weightlifter. He is transferring chemical energy stored in his muscles directly into gravitational potential energy as he forces the bar upwards. Or look at the boat. It's transferring chemical energy from burning fossil fuel into kinetic energy to pull a skier across the water. In physics, when a force moves an object, work is done. It's that simple. Work done is simply the scientific measure of the energy transferred. You calculate it by multiplying the force applied by the distance moved in the exact direction of that force.
We can actually walk through this energy transfer process step by step to synthesize everything we've covered today. Imagine a simple circuit lifting a block. First, chemical energy is safely stored in a battery. Second, an electric current actively transfers that energy along the wires to a motor. Third, the motor then does mechanical work to lift a physical weight against gravity. And finally, step 4, that weight gains gravitational potential energy. It's a continuous, beautifully logical flow of energy from one store to the next, entirely facilitated by the concept of work. See how it all connects?
I want to conclude with this provocative thought, and I really want you to do this. Look around your room right now. Seriously, look around. Where are energy transfers happening, and what specific stores are involved? Is it the thermal energy radiating from your computer, or maybe the kinetic energy of a ceiling fan? Spotting these physical principles operating in your everyday environment, not just on a textbook page, is what will truly cement your understanding of the universe. And understanding the universe is how you ace these exams. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.